Hello, welcome to this session on engineering mathematics. My name is Russell, and I'm going to be going through it with you guys. This is going to be a Menti session. So you may or you may not be having a code like the one you see on the screen here, or a QR code that you would use to interact with the session as we're going along. So let's start. This session is about engineering mathematics, what it is, why it's helpful, and how we do it here at the University of Bristol. I'll start by presenting myself. I'm Russell. I'm originally from a small country called Cameroon. This is in the middle of Africa. And yeah, I love traveling. So I've traveled throughout my undergraduate degree in the search of what I really liked, my passion for science. I love football, I love movies, and yeah, I love planes as well. So now it's up to you. Please tell me something about you, uh, so that we can just break the ice. So I will show you some of the answers, but then you should pause here and then you should turn away from this screen, and if you have a Menti code like the one you see up here, you should type in something about you. Tell me something interesting, or your favorite food, maybe your favorite subject. Um, Essentially anything, anything you might like. The answers that you see on the screen at the moment are just examples of some of the things that some of the you guys, some of the things that you guys in the audience might be interested in. Mm. So I'll give you a minute to think, and then let's come back to this. Okay, you should have typed everything. I can see that some of the examples of the things that some of you guys might be interested in are movies like Interstellar, great movie, chess as well. These are fun activities. Traveling and reading, very much like me. Robotics, this is very these are things that are very these are things that are done a lot in the School of Engineering Mathematics here at Bristol. Painting, these are more artistic endeavors, IT, animes. There are quite a lot of interesting things that you guys are saying here, which is very interesting. This means we have so much in common, and I also see this a huge diversity of hobbies here, huge diversity. So that's very interesting because it's gonna help. It's gonna come back later. I hope you keep showing me this diversity in the future, in the future questions. This is something that always comes up with these sessions. So I'll tell you about my background, how I got to do what I'm doing here now. My A level was in mathematics and physics. I did a little bit of chemistry as well, and lots of computer science. So it was a all-out STEM A levels. And then I did my undergraduate in mathematics. My my graduate studies were in applied mathematics, and now I'm doing a PhD in machine learning. And I did this a bit all over the world, like I showed in my earlier slide. And this is I kind of want to use this to show that in STEM or in engineering mathematics, there are different paths that can lead to the same outcome. You can start in mathematics, and you can still end, and you may still end up in a PhD as a PhD student in machine learning, or you might start in computer science. You may still end up at the very end of your career in machine learning, or you can start in chemistry and you can still end up in machine learning. So this is kind of to say that essentially uh STEM, it's as long as it's STEM and as long as you're being taught critical thinking, analytic logical thinking, these are applicable to many other areas. And we're going to come to see that about engineering mathematics as well. So What is engineering mathematics? I keep talking about this thing called eng math. What is it? So this is essentially the art of applying mathematics to solve real-world problems, easy and complex real-world problems. What you do, how do you do that? Is essentially you want to combine theory and practical engineering skills. So you combine these and you use computers when you cannot really solve these problems by hand. Um, Now, there is a need to address today's technological problems. If you're applying mathematics to solve yesterday's problem, it's not really engineering mathematics. These are engineering problems. Uh, Engineering is problem solving. You need to be solving a problem. So if a problem has already been solved, it's not really, you're not problem solving anymore. Unless you're bringing in a new solution, a new approach. That is amazing. That is engineering mathematics. So, so essentially, in a few words, engineering mathematics is applying maths to solve real world problems. Now, the way I framed it, you might think, oh, engineering mathematics is just mathematics in the real world, because that's the way I said it. But it's actually more than that. It's mathematics, it's data science, it's artificial intelligence, it's engineering, it's healthcare, it's robotics. Like that, these are themes that are present here at Bristol. And all of these interdisciplinary ideas, you want to bring them to the real world. It's not just maths. Like I showed with my background earlier, I came from a math background, but I did lots of chemistry. I did lots of computer science in the past. I did lots of mechatronics as well, and that all led me into this PhD career. So it's all of these these it's all of these disciplines that you get to use to solve real world problems. Um, For example, these are some of the problems that we can solve with engineering mathematics. I have a colleague who uses brain signal. He records brain signal and try to tell what people are thinking or doing just based on the signal recorded from EEG on their brains. Um, So this is very interesting. These are very interesting things to do. I think some of you guys might remember a few years ago during the coronavirus pandemic, um, mathematicians were used a lot. They were required to model the spread of this terrible disease. It all came down to this small number called R. If R is bigger than one, it means the disease is going to keep growing and keep infecting more people and killing more people. We don't want that. But if R is smaller than one, like in this case, R is 0.7, 0.9, in this range, the disease scientists were able to keep the disease under control. It doesn't reproduce that much. It doesn't infect that many people. And that's why today we don't hear about coronavirus that much, even though it's still very much a problem. The robotics, I'm pretty sure some of you guys are very interested in robotics. This is something that there's also social media. With social media, and you can have your friends and networks. These are all models with mathematical graphs. And in a graph, you are a node, and the connection between you and another individual might be a friend. That's an edge. That's an edge of the graph. You can have a different kind of connection with someone. Someone might be your parent, or you might like a page. That's a different kind of connection. And these are all models in maths, and engineering mathematicians just love this. You can also use engineering mathematics to solve problems that relate to blood flow, fluid simulation. So as blood is flowing inside your heart, engineering mathematicians can model this and tell you whether you're healthy or not, whether you need to have a look at your heart or not. And this is very important. So there's a whole variety of problems that we can solve with engineering mathematics. But obviously, I couldn't list them all. There's just too many. So I want to get your help on this one. Can you tell me what problems you think we might solve? So this is where you maybe turn away from the screen again and then look at your phone or your computer and use if you have a Menti code, type in one real world problems that you can think of that we might maybe solve with engineering mathematics, or maybe not. That's not really the target here. Just real world problems, and let's discuss whether we can solve them. Okay, I'll pause here. Okay, that's enough. I guess you've had time to write some of the problems I think we can solve, and I'm pretty sure you guys came up with some really interesting things. So let's just review some of the answers that I've heard. Um, Pollution, I can see, yes, air pollution, noise pollution, visual pollution, climate change, that's a very important one. That's one I personally tackle in my research as a PhD student. So I really love that suggestion. Segregation. Oh, I can see the way one can model networks of people and then see why and how can we solve these issues. This is just really, really important. And I like the thinking here. So I'm sure some of your thinking is maybe along the lines of the answers that I'm seeing here. So let's just go with them, okay? Energy crisis. Yes, yes. We won't always have oil and gas. We need to be looking for other sources of energy, and mathematical models are really important for that. Housing. Housing crisis, yes. Class system again, overpopulation, inequality, health and safety. Absolutely true. Absolutely true. Um, Flight emissions. Again, I can see a theme of sustainability that's coming across, which is really just really interesting. And um, so yeah, these are just some of the examples. And I promise you, if you can think of a real world problem, you can think of a way to place an engineering mathematician in there. And if an engineering mathematician it hasn't been used yet, then probably you're not doing it right. Then you probably need to hire an engineering mathematician to give you that perspective and mathematical model. So now let's go a bit more into the details now. We've just been talking about what can we do with this thing called engineering mathematics, and but what's the degree like here at Bristol? So obviously in engineering mathematics, there's mathematics. So you will be doing some mathematics, some algebra, calculus. But as we discussed, mathematics is not everything. You need to be doing some modeling. What's a model? We look into computing when you cannot really solve your problem by hand by writing down the solution of your equations, for instance. You leverage a computer to help you with that. And very importantly, engineering. You need to leverage engineering from civil engineering to mechanical, electrical engineers. You need to talk to these people and then get them all to converge to a solution. So you can see that this is interdisciplinary problem solving. All these ingredients converge to a problem solving solution that involves many components, and you get a more robust solution if you think like this. Um, a mathematician alone without an engineer, the solution could be too abstract. It wouldn't fit the real world. An engineer without a mathematician, the solution might not be strong and robust, and the calculations might not be right, right? You want to use the mathematics and the engineers and leverage the computing and build some really good models. So we'll look into that in a bit more details. So what is engineering mathematics? That's pretty clear now. I avoided the question of what is a model. So now let's look a bit more about let's talk a bit more about modeling. So the degree of engineering mathematics here at Bristol relies fundamentally on mathematical and data modeling. This is a unit that's central to the degree. So it always starts with a real world problem. I think we've established that by now. You get the real world problem, and then how do we solve it? First of all, you need to analyze and interpret the system. Analyze and interpret. You need to talk to people, analyze, get every information you can on the problem that you're trying to solve. And from there, you need to create a mathematical model. So a model is, think of an equation that describes your phenomenon that you're trying to explain, right? Think of it as a software that simulates how your system is going to evolve in time. Think of it as a summary of your problem, a description of your problem that makes sense mathematically, right? It's not just words. Um, Now, once you have that model, the next step in this very important pipeline is to solve the model to make predictions. Now, you can solve the model by solving an algebraic equation, or you can use a computer to solve the problem. There are other ways, but the idea is you need to try and solve the problem to make predictions about the future or cases that in settings where you don't have data. Now, once you make those predictions, you need to compare them to reality. And this is a very, very important step. I cannot stress this enough. You need to compare the predictions you make with reality. And from there, you have two possible outcomes. If your comparisons are really, really good or conclusives, if you get conclusive comparisons, conclusive, you can just deliver your conclusions from there. Your model was good, um, it fits with the reality, you deliver your conclusions. Or if the model is bad, you go back to analysis of the problem, right? Because you might have forgotten something. You might have forgotten to talk to the engineer that that is the person that really knows the problem. You might have forgotten to take into account one variable that really impacts the whole problem. So you need to go back, analyze, collect more data, and interpret the system more. I want you guys to have this diagram in your head because this is going to come back again and again. This is very, very important um, diagram, mathematical and data modeling. Now, I want to stress that this first part, from going from the real world problem to analyzing and interpreting the system, this is what we're going to be focusing on. And how do you achieve that? You just get to ask questions. You get to talk to people. You get to talk to the engineer. You get to talk to the computer scientist. You get to talk to the domain expert in the problem. You get to ask questions. And that's what we're going to be looking at today. Obviously, I cannot teach you guys how to create models in an hour-long session, right? So let's just do this first part today. Let's learn how to ask questions. Now, before that, let's talk about some of the skills that you think you might need in order to solve these problems. Um, Essentially, you see the diagram that I just showed you. See this diagram. What are some of the skills that you think you might need if you were to join and join this degree um, in order to just get through this pipeline? Now, think you get to pause again, look at, take your phone. If you have a Menti code, try and type something. Try and write down if you have a piece of paper in front of you, and we'll look at those later. Pause from here, and I'll wait. Okay, I've waited quite a long time. So now, these are some of the skills that I've collected in the past, and I think they are very, very valuable. So I'm gonna just read a few. You could essentially, you should ideally be really good at problem solving. Problem solving is the engineering part of engineering mathematics. Engineering is problem solving. It's coming up with creative solutions to problems, right? You need to be resilient, yeah, because when your system fails, when you compare your model or your answers to the reality and you see that it doesn't work, what do? You don't give up. You go back to the drawing board and you analyze again. So you need to be resilient. It's good to be a critical thinker. Yes, you need to be you need to question everything, open-minded as well, right? Yes, you need to be open-minded and take advice from every stakeholder. You need to be organized, you need to be dedicated and good at time management. Indeed, when you have so many components to juggle, you need to be good at decision making, which connects very well with the time management idea. So these are some of the skills that you will need. And with this, I think you guys have those skills, or if you don't have those skills, think of it like these are skills, these are acquired skills, right? But we're gonna put some of those in practice. Some of the skills that I'm sure you guys have. I'm sure you guys are resilient. I'm sure you guys could learn how to manage your time. So let's solve a problem. It's a very simple one. Um, the problem is that the Bristol authorities are building a minor injuries unit for a very small hospital. They they don't know what the best number of chairs to have in the waiting area. So they don't know. They they want you, the engineering mathematician or upcoming engineering mathematician, to tell them what that number of chair would be. So you have essentially a minor injuries hospital. Think of an emergency unit, uh, but um, just built, newly built. We want to put some chairs in that in the waiting area, but we don't know the number of chairs. We need you to tell us what's the ideal number of chairs. So I'm going to ask what is the number? What do you think is the right number? Okay. I'm going to wait a little bit and you should look at your Menti and then type in a number. What's the number? What do you think is the right number? Mm, okay. From 0 to 100, I'm I can see, and I'm pretty sure that the answers are very spread, right? Some of you may be thinking, oh, we should have zero or close to zero, like 5 or 10 chairs. Some of you might be thinking we need 100 chairs. Some of you might be thinking we're more like in the middle, 50. So the answers are all over the place, and this is exactly the point. You don't have that many. You don't have that many questions resolved yet to know what's the ideal number of chairs, right? You need an engineering mathematician to help you with this. Now, what questions would you need in order to analyze and interpret the problem? This is the first part of the pipeline that we talked about earlier, right? You have a real world problem. You need to find out what's the ideal number of chairs, and you need to now ask questions to essentially understand and analyze the system. So this is where you turn away a little bit again, and then don't look at the answers here. Take your phone and then just type, what are some of the questions that you would need to know? I'll wait a little bit. Are you okay? Okay. Okay, so I'm pretty sure you guys have some good, interesting questions. So let me just read some of the questions that I think are very pertinent. How many people come with the patients? Yes, uh, the patients are usually accompanied by loved ones. So how many people usually come in with them? You need to know that if you're if yeah what's the room size? Yes, I said it's a very small hospital, but what's the size really? You just this is very important. What's the population of the area in which the hospital is in, right? You need to know that. How many people are oh, I'm guessing this is how what's the staff? How many people work in that hospital, maybe? Or how many people come in and out usually in a minor injuries hospital? Yes. Um, yes, how many people per room? Yes, if you know the number of people in the room, maybe you need to know the number of visitors and all that. Yeah, how many people are you expecting to visit per day? Yes, you need to find that number out. You need to ask that number to the people that build the place, right? The Bristol authorities. How busy is it on average? Oh, I like this one. What's the budget? What's the budget? How much money do you have to buy chairs? You need to take that into account. This is very important. Um, what's the average waiting time? Yes, if the hospital is very busy, waiting time will be long. Otherwise, you don't need that many chairs. What are the statistics of minor injuries and what are the timings of rush period in that hospital? Yes, yes, a very long one, but I like it's a very specific and detailed question, so you need to learn to ask pointed questions like this to understand the problem. So you need to know these statistics, essentially like average, maximum number of people, minimum number of people, the overall spread. Very important. Um, the age range, very interesting. What's the age range of people in the area? Because if the people are more elderly, they will need to sit more, I suppose, to if they were younger. So yeah, these are some of the questions that you would ask. Um, so now let's turn our attention to some of the tools that we could use to address those questions. I'm going to wait a little bit and then let you type in some of the tools that you think we might use. Okay, I think you might have typed in a lot of tools. So now let's review some of them. Some of the tools that you might use, you might need a modeling software, yes, because when you collect all of the information that we said, if you know the number of patients, if you know the size of the room, if you know your budget, then you probably wrote down a few equations, and you might need a modeling software to run to run those equations and see what the output is. Um, you might need Excel to graph the data. Very, very nice, very interesting. You can ask AI. AI, yes, you could ask AI, but AI might just do all the job for you, right? You need to find something to do. And AI might not be very sure as well, like reliable. How do you trust the results that the AI is going to give you? You need some documentation tools. I like that. You need surveys. Yes, you need to send out surveys, ask people, maybe the staff, what do they think is the average wait time if that number is not around. You need some sampling methods, statistics. Yes, spreadsheets again. You need a blueprint, a copy of the room, blueprint copy. Very nice. Yes, you need a bird's eye view of almost everything. So these are some of the tools that you could use to answer these questions. Very interesting. Um, Again, let's look at how could we check our answers now. I'll pause here. Okay. To check our answers, I say this is a very important part of the pipeline, right? Once you've um, analyzed the problem, you've built a model, you've used these tools that we've talked about. How do you check that your answers are actually correct? You could ask the hospital staff. Yes, that's one way. Yeah, is this usually how things are? Is the numbers that I forecasted, are they the correct ones? You could show that to an expert, a co-worker, or an expert working in that area of modeling wait times, essentially. You could do simulations. Yes, you could compare against some really, really high quality simulations from expert models, like really good models that were validated by many people in the past. You could compare your predictions against those, even if those are not perfect, right? You could you could, yeah, peer review, repeat the experiment, check if you have the same result with other methods. Absolutely true. Yes, you need to come up with some baselines and then just like do it, repeat the experiment again with different, I don't know, different, you vary the tools a little bit. You need to research online. Yes, yes. You need to get all information. I think that's a very important one, actually. Research online, but while researching online, you need to make sure that the setting is the same as yours. Or if the setting is different, you need to be sure, like, make sure that you can adapt the setting. Again, you can use AI, which is very interesting. And you can also see previous patterns and data before. Yes, definitely compare against what happened in the past. See if you can predict what would have happened in the past and then see if you predicted very well, right? So essentially use previous historical data to check if your model is doing well. Um, that's very nice. So lots of suggestions. Um, well, I think that was very good. We solved one problem. There's another problem. This one is going to be mostly me talking, but this is the one that I care a lot about because this is my PhD project. This time you are tasked with predicting what the weather will be tomorrow and in the next few weeks, right? It's a different problem. This is classic problems that engineering mathematicians deal with, and AI scientists deal with, machine learning scientists like me. It's all engineering mathematics. So first of all, why would we want to predict weather? To know what to wear, for instance. Yes, to know what happened in the past as well, like yeah, for historical reasons, right? Maybe. Well, that's interesting. Um, Please type your answers, okay? Just be typing in your answers. Um, Preparation, safety for quality of life. Absolutely. These three are very important. You need to know extreme events. You need to know if they are, if there's what's the risk of them killing people, right? They can be quite devastating. And when they happen and we're not ready, it's just the devastation is just unbearable. So we need to be aware of that. That's why we need to predict weather. What do you think affects the weather most? A bit like before, right? When we have a problem, we need to ask questions. We need to think what impacts the situation. With the chairs, we asked a lot of questions. In this case as well, we need to ask lots of questions. So what affects the weather? Humidity, temperature, wind speed, butterfly effect. I like that. That's very mathematical. Yes, a butterfly flapping its wings in Brazil affects the weather in Europe. How come? Right? Greenhouse gases, yes, it does very much so. Past trends, yes. The rainfall, you need to take all of this into account. And then modeling is essentially putting all of these ingredients together, finding out how does this impact my desired variable. And then it's like making a soup, you're just putting in ingredients and then you come up with a model. A model in this case is a set of equations and we call them the Navier-Stokes equations, and they model how fluid, in this case air pressure, velocity, how they evolve in time. If we know the state today, how would the air pressure at one point be tomorrow? But this equation is really difficult to solve because it has so many terms and very lots of complicated derivatives. So usually we use a computer and then we solve it. Um, Now, how do we check whether our predictions are right? This is a bit like in the previous case. We simply ask people, we compare against what happened in the past. If our model is able to predict what would have happened in the past, we need to just talk to the domain experts, like compare against real observed data. So yeah, that's a bit how I use engineering mathematics personally in my own PhD. I learned to ask a lot of questions. I learned to ask what are the events that impact weather. I use these tools to and really big computers to simulate these events. I want to leave you guys with this diagram, the one we talked about, engineering mathematics, uh, mathematical mathematical modeling. You get a real world problem, you get to ask questions. You must ask these questions. You analyze the problem, you interpret the problem, you create a mathematical model. This can be a set of equations, this can be a software, this can be it can be many things. But then you need to solve that model. Solve the model doesn't mean you have to solve equations, right? If the equations are too hard, you can use a computer and big ones. In Bristol, we have some of the biggest supercomputers. You can use them to solve your model. And then when you solve the model, you need to compare your results with the reality. If they are good, you deliver your conclusions to the Bristol authorities or to whoever asked you to create that model and to understand that problem, right? But if they are not good, you need to go back and reanalyze and reinterpret the problem. So that is the cycle of mathematical modeling. It's a very, very exciting time to be an engineer mathematician. Essentially, that's it. Thank you very much for listening to this session. Bye-bye. Have a good time, guys.